the last chapter we talked about conservation of energy, so let's talk about that now in the framework of collisions. If we have a collision where two balls are approaching each other and they undergo a collision, momentum is always going to be conserved in all collisions. However, energy is not always conserved, and when energy is conserved, we have a special name for this type of collision. It's going to be called an elastic collision. If you simply look at the length of the velocity vectors a and a prime and b prime, you can see that they're the same lengths, and what that indicates is that energy has been conserved. So by definition, this is going to be an elastic collision. If you now consider the bottom case and you take a look at these velocity vectors, then they're a lot smaller. Clearly, energy has changed, energy being related to the velocity. So energy is not conserved in this type of collision that we're going to call inelastic. And we'll talk more about each one of these types of collisions in the next couple of slides here. So here let's consider elastic collisions, and only in one dimension. So here we have a collision occurring between two objects with mass and velocity. Let's say that we know everything over here. And then when a collision occurs, I know that it's elastic. I still know the masses, but what I'd like to know is how fast are each of these guys moving. So how to solve this is I know that momentum is always going to be conserved. The momentum before has got to be equal to the momentum afterwards, and I can write what the momentum is. It's going to be the mass of A multiplied by the velocity of A plus the mass of B multiplied by the velocity of B. These two guys put together are going to be the momentum beforehand. As for the momentum afterwards, that's going to be the mass of A multiplied by the velocity of A prime plus the mass of B multiplied by the velocity of all B primed. Now, I also know, and I don't know this and I don't know this, so I have one equation and I have two unknowns, but I do know that the kinetic energy is going to be conserved. So the kinetic energy before has got to be equal to the kinetic energy after. So I can go ahead and I can write that out. I can say 1/2 mass A, velocity A squared, plus 1/2 mass of B, velocity of B squared. That's going to be the kinetic energy beforehand. That's going to be equal to the kinetic energy afterwards, which is 1/2 mass of A, velocity of A prime squared, plus 1/2 mass of B, velocity of B prime quantity squared. And in this equation, I have one equation and two unknowns, but now I have two equations and two unknowns. I can go ahead and I can solve this guy and figure out a relationship between the velocities. The book does this in section 7.5, and at the end of the day it says the velocity of A minus the velocity of B is going to be equal to negative velocity of A prime minus velocity of B prime. Now we can use this to solve for one of the velocities and help us solve our collision problems. If we now consider inelastic collisions, we know that energy is going to be lost. It's going to be lost to thermal energy, it could be lost to potential energy, or it could be gained. If we had a rocket that is going up on some are going up, say, in that direction, and that rocket exploded into two different pieces, then there was some additional chemical or nuclear energy that was added to that process. So the energy of the system has, in effect, changed. One very special type of collision would be completely inelastic, and in that case, the objects stick together afterwards. And that adds a little bit of a bonus because now we only have one final velocity to solve for. We still would say that the momentum beforehand is going to be equal to the momentum after. If we consider the case of this ballistic pendulum, where we have a bullet going into a mass and then these two masses stick together, we would write the momentum of the system beforehand to be the mass of the bullet multiplied by the velocity of the bullet, in addition to the big mass m multiplied by the velocity of that big mass m. The momentum afterwards is simply going to be those two masses added together, as well as one final velocity, v prime. In this particular case, we know that this mass was initially at rest. So what we can do is we can say the mass of the bullet multiplied by the initial velocity of the bullet must be equal to the sum of the two masses, little m plus big M, multiplied by v prime. Suppose I know what this initial velocity is right here, and I know the mass of these two bullets. I can now solve this guy for the final velocity v prime. And if I happen to know that final velocity v prime, then I can go ahead and I can use energy conservation and say, now I have this mass and some velocity right here. I know it has some kinetic energy. How high is that block going to go? Well, that block is going to go up to a certain point. All of the kinetic energy will now become potential energy, and I could actually go ahead and I could solve for the height of that guy. So I can measure the height of a pendulum like this and work backwards and solve for the velocity of my bullet if need be. I would work backwards, solve for v prime, and then solve for my velocity using this equation right here, using conservation of momentum. So kind of a neat blend of momentum and conservation of energy in one pretty nasty looking inelastic collision problem. Collisions in 2 or 3 dimensions are actually simpler than you might initially think. All we have to do is we need to treat these 2D problems as 2 one-dimensional problems. So for off-center collisions, we can still use conservation of energy if it's an elastic collision, and we can always use conservation of momentum. All we would have to do is we would say that the momentum beforehand in the x direction is going to be equal to the momentum afterwards in the x direction, and similarly the momentum beforehand in the y direction is going to be equal to the momentum afterwards in the y direction. In a case like this, let me simply just take a look at the x direction only. I would say that the momentum beforehand is going to be the mass of A multiplied by the velocity of A, all in the x direction here. I have no y component. And the momentum afterwards is going to be the mass of A multiplied by the velocity of A, now only in the x direction, plus the mass of B multiplied by the velocity of b, now only in the x direction, I know what these relationships would be because I know these angles theta A and theta B. I am very good at breaking vectors up into components. So we would do the same thing for the y direction, and the math would become quickly unwieldy. However, it's very easy to formulate these problems. So let's shift gears a little bit and talk about the center of mass. Up until this point, we've been dealing with, let's just say, boxes or balls. And we've said, suppose I take this box and I throw this box. It's going to go up, it's going to come back down, and it's going to land at the ground. What we've essentially been doing is we've been boiling all of the mass of this box into the center of it, and we've been describing how this particular point of the box behaves. We know that it's going to have some parabolic motion. This particular point is also known as the center of mass. And in the case of my box being thrown, then I'm considering only translational motion. However, if we take something and we throw it and we spin it, then we can also have rotational motion. And it turns out that if you throw an object and you set it spinning, it's also going to rotate about its center of mass. So if you take a look at this wrench right here, its center of mass is going to obviously occur nearer to the head than to the butt end of it. So it's going to be represented by the X in these pictures here. And if you set it, if you dropped it, or you set it going in this direction right here, so here it has its translational motion, it's also going to have its rotational motion, both of which are going to occur about the center of mass. So kind of looking at the snapshots of this wrench, you can see that it's moving equal distance in equal amounts of time. So it's traveling with translationally it's traveling at a constant velocity, and it's also rotating now about its center of mass. So how do we go about calculating the center of mass? If we take a look at the picture I have down here, here we have a mass. It's at some certain distance away from, I'm going to say, my origin, and here we have some mass right here that is further away from my origin. I know that if I set these guys spinning, it's going to occur somewhere in between the two of those. And actually, something else about the center of mass is that could be where you would balance an object at. So if you set your finger exactly at the center of the mass of the system, then it should balance perfectly at that point. Think about a yardstick. It's most likely going to balance in the middle because it has equal amounts of mass on each side, at least if the wood is constantly dense throughout the entire yardstick, which may or may not be true. So how do we go about calculating these guys? It's actually quite simple. The center of mass in the x direction is simply going to be the first mass multiplied by how far away from the origin it is, added to the second mass plus how far away from the origin it is, divided by the total mass of the system, mass A plus mass B. This can be generalized to add in a third mass. If I had a mass C way out here at some distance x sub c, then I would simply add mass C multiplied by xc, and then add mass C down here, and so on and so forth with masses D, E, and F, etc., etc. This can also be applied to the y direction, where if I had a mass here at some distance y, then I would also say that the y center of mass is going to be the mass c, now I'll call this one c, multiplied by some distance y sub c plus some mass d plus multiplied by y sub d. Divide all that guy by mass c plus mass d. And right here I'm going to put my mass d way down here in the negative y direction. I would of course take that into account when I calculated my center of mass in the y direction. The center of mass is actually quite easy to find experimentally. If you take an object and you hang it from different points, in this case we have a white hole and a black hole. If we hang our object, stick a nail through it, and draw a line straight down using the white hole, do the same thing with the black hole, hang it up on a nail, draw a line straight down. Here's the line from using the white hole. Then my center of mass is going to occur where the two lines intersect. And the book also talks a little bit about this thing called center of gravity. For everything that we're going to work in this class, the center of mass will be equal to the center of gravity. The difference between the two of those is that the center of gravity is going to be the point where gravity acts upon. These two are identical for everything that we're working on, because they will be unless gravity acts differently upon parts of the body differently, which could be the case if you had really large objects that were sticking up in the sky, but we'll leave that for future physics classes for you. We can take a look at calculating the center of mass for the human body simply, or in the first case, looking at a leg that is extended. Here I have the center of mass for the thigh, and here I have the center of mass for the calf, and here I have the center of mass for the foot. All of these guys acting at different x positions. I can use that equation for x center of mass to calculate out what the center of mass should be, and I'm going to come up with a center of mass for the leg to be right here just above the knee, which is perfectly reasonable. Now if I go ahead and I bend my leg, now I have the center of mass for my thigh. That's virtually unchanged, 9.6 units away from the top of the leg. Now I have my center of mass for the calf located at 23.6, and the center of mass for the foot also located at 23.6. So when I go ahead and I say my x center of mass is equal to so on and so forth, now these distances are going to be the same. In addition, I'm going to have some y center of mass that's going to need to be calculated, and I'm going to say that the thigh, or I'm going to say that might say be my y is equal to 0 point. I can go ahead and calculate all these guys out. I know what their y positions are right here of my center of masses. Now I'm going to have some center of mass that's going to have some x component and some y component, and obviously that's going to be outside of the leg. That's going to occur out here. That is perfectly reasonable. There's nothing that says that an object's center of mass has to be inside of that object. If you think about a donut or something like that, the center of mass of the donut is going to be in the middle of the donut, where there is no physical mass of the donut. However, that is the location of its center of mass. And in fact, a high jumper, they want to keep their center of mass as low as possible, because that is related to how much force and how much velocity they must push off from the ground, because their translational motion is going to behave at the center of mass. So what they do is they bend their body as they go over the bar, such that their center of mass actually doesn't go over the bar, but passes under the bar. Now it turns out that we can do some really fun math with the center of mass and the translational motion. If I go ahead and I rewrite my center of mass equation from the previous slide, that the center of mass is going to be mass of A multiplied by some position of mass A plus the mass of B multiplied by the position of mass B. I've multiplied out the total mass of the system right here, big M, which is going to be mass A plus mass B plus mass C, and so on and so forth, if you will. Let me now recall that the velocity is going to be equal to the change in position divided by the change in time. Let me consider now that my particle is moving, and so my positions are now changing. I can also write my change in position is going to be equal to the velocity multiplied by the change in time. So I can rewrite this equation to be the total mass of the system multiplied now by the velocity change in time. This is the velocity of the center of mass. That's going to be equal to the mass of A multiplied by the velocity of particle A change in time plus the mass of B, velocity of particle B multiplied by the change in time. And lo and behold, these changes in times go away. So I've essentially written the total momentum of the system being related to the total mass of the system and the velocity of the center of mass in this equation right here. I can of course take this a step further and say now my system is accelerating, and so the velocity is going to be changing, and a change in velocity divided by a change in time is going to be equal to the accelerations. All of these velocities are now going to become change in velocities, and I can write the change in velocity to be equal to the acceleration multiplied by the delta t right there. So I can take that equation and rewrite it down here. Mass multiplied by the acceleration of the center of mass multiplied by delta t is going to be equal to the mass of A multiplied by the acceleration of A multiplied by delta t plus the mass of B multiplied by the acceleration of B delta t. Same thing, I cross out my delta t's, and now I have an expression for the acceleration of my center of mass. And if I take a look at what these guys are, that's simply equal to the net force acting on the system. So the acceleration of the center of mass can simply be expressed as the net force divided by the total mass of the system. Lastly, just a summary slide. Feel free to pause and just reflect on anything that strikes you.